could draw a position versus time graph, velocity versus time graph, and acceleration versus time graph of something dropping. Okay? Something. And up is the positive direction, and we're ignoring air resistance. Grab that. Thanks. Okay. Everybody good with that? Now I want the motion graphs of this after it leaves my hands before I catch it. I'm tossing the ball up. What does that look like? Up and down. What does that look like on position versus time graph, velocity versus time graph, and acceleration versus time graph? Nope, up and down. This whole process. But not my hands. Okay, I'm going to do this. And a motion detector. See what we got. Ready? Oh, that was so close to being good. Oh, that's pretty. Okay. Notice. Okay, acceleration versus time graph. I've zoomed quite a bit in. But here are the shapes. Notice the value of acceleration. Okay. Now, in case you didn't see that, initially it starts fast in the positive, slows down, turns around, speeds up in the negative. Something like that. Initially it starts fast in the positive, it's going up quickly. And as time goes on, it slows down. And then stops at some point, turns around, and speeds back up in the negative direction. Acceleration. In the first part, you're slowing down in the positive direction. And then you're speeding up in the negative direction. The value of this is going to be what? Should be close to negative 9.8 meters per second squared the entire time. Okay, looking at the average here. Negative 9.57. Pretty close to negative 9.8. Thank you. Good with that? Okay. At the highest point, it's at rest. How long is it at rest for? Just a moment. The time right before that, was it moving? Time right after that, was it moving? So from moment to moment to moment, your velocity is changing. That is why you still have acceleration, even at the highest point. Good with that? Talk to your neighbor.
Oh, right. Yeah. I was just looking at the graph. I mean, that makes more sense.
All right. What do you say? Correct answer is C. Staying constant. And that value is 9.8 meters per second squared downward. If you were tempted to say increasing or decreasing, specifically decreasing, then you're getting confused between acceleration and velocity. Okay? Velocity of magnitude is decreasing, but the rate at which it's decreasing is constant, and that's acceleration. Okay? Okay, this question is a warm-up question, not meant to be tricky. Is everybody okay with B, the thrown rock? Here's the real question. Same scenario, just different question. Which rock has the greatest change in velocity during the first second? Have a conversation. All right. What do you say? All right. So after this one leaves my hand, what forces are acting on it? Gravity. After this one leaves my hand, what forces are acting on it after it leaves my hand? Just gravity. Okay. No air resistance. We're ignoring air resistance. After it leaves my hand, I no longer exert a force on it. Okay. Just the force of gravity. Both are in free fall. Both are experiencing an acceleration of 9.8 meters per second squared downward. Both experience, I'm going to round that to 10, both experience a change in velocity of 10 meters per second every second. The dropped one goes from 0 to 10 meters a second in 1 Mississippi. The thrown one, I'm going to make this value up, goes from 30 meters a second to 40 meters a second in that 1 Mississippi. Both experience the same change in velocity during that 1 Mississippi time interval. Okay, they have different final speeds. Yes, the thrown one is definitely going faster, but they both experience the same rate of change because only the force of gravity is acting on them. How are we doing with that? No, you can say like I don't like prove it.
No, it's fine. I just don't understand if you're like throwing it and it goes faster, how the velocity is.
No, it's good. No, this is what needs to happen because you're not the only one. I guarantee it. I just read your face better. Okay, so after it leaves my hand, just like this going up, is there a force of gravity? Sorry, is there a force from my hand? Is there applied force going up after it leaves my hand? It's just the force of gravity causing it to slow down. If I throw it down, just like going down after it leaves my hand, I no longer exert a force on it. It's moving fast. Yes, it is. But the only force acting on it is the force of gravity, causing it to experience an acceleration. That same force of gravity is acting on the one that was dropped, causing it to experience acceleration. They both have the same rate of change of velocity. And so if they fall both for the same amount of time, 1 second, they're both going to experience the same change in velocity. They're going to be different places on the speedometer, but over that 1 Mississippi, they'll both change the same amount of 10 meters a second. Suggestion, you could do the math, but draw a velocity versus time graph. Okay, the whole time would be 3 seconds. Look at half the time on your graph. Does that correspond to half of the velocity? So your velocity versus time graph should be a straight line. At 3 seconds, you should be moving at 30 meters a second. At half of that, does that look about half? That's because this is a straight line. The velocity is changing at a constant rate. So at half of the time, the velocity is changing only half as much. Okay, so that's another way you can do it, is using a motion graph. You could do it with plugging in numbers in kinematic equation, finding that value. Last question of the day. Okay, the rough part about this question is I'm asking for half the, dependent upon half the distance. Oh no, did I jump over that? I did, that's what happened. Okay, for this one, position versus time at half the time, we've only fallen this far. Good with that? Okay. Um, less than half the distance. Okay. Sorry, I lied. There's one more. My suggestion is you're going to be using both of those graphs that you just drew. For the sake of time, here's the whole, here's half. Was that half the time? Way more than half the time. There we go. Does that make sense? So at way more than half the time, oh dear, that's all wrong. At way more than half the time, you're going faster than 15 meters a second. Remember, you got a worksheet due tomorrow.